Very. Okay, let me share my screen. Just the right one. Okay, you can see this, right?
Yes.
And I can also see the chat window too. And I just want to say that, so this talk is a little bit different than most talks I've given. So this is just kind of pulling together some work that I've been doing just to out of curiosity. I haven't really written a paper about it, but the invitation for this talk was a really good forcing function for me to go in deep on this topic. And I really appreciate the opportunity to be able to share this with you today. So that said, so it's a little bit new, so feel free to ask questions if anything is unclear in the middle of the talk, as well as we can have a more extensive discussion at the end. And I have the chat window open, so you can put questions in the chat, or you can just interrupt me with questions. They are totally welcome. Okay, so I want to talk about implementing the lambda calculus today. And the other thing I want to point out is that all of the material that backs up this talk is all available on GitHub in the repository at the address at the bottom of the screen. So if you're interested in this topic, you can definitely check it out more deeply afterwards. Okay, so I'm talking about implementing the lambda calculus. And when I say implementing the lambda calculus, what I really mean is implementing capture avoiding substitution. It's that thing we kind of teach in the very first week of our classes. And we might say things like, you have to be careful when you're doing substitution in the lambda calculus. For example, say you're doing a substitution like this, where I'm replacing the variable z, and I wanted to replace it with y. In this term, z applied to lambda y dot z, we have to be careful of capture, because that second z in the term that we are substituting into is underneath a y. When we do substitution here, we have to rename that bound variable so that it doesn't capture the y, the free variable that we're substituting in. So this is a simple, but it's a really devilishly intricate idea, especially once you start to think about, how am I going to implement this? If I want to implement the lambda calculus, how can I make sure that I do this correctly and efficiently? And so when I'm talking about an implementation, I'm really talking about taking something like a data type that looks like this, where I'm doing the lambda calculus, so I have a case for variables, for lambdas and application. But right now, I'm not going to nail down how I'm going to represent variables, right? We're gonna see there's lots of different ways that we could represent the variable type. And there's lots of different ways that we can represent the binding type. And these two things can work together as we implement our substitution function, as we write a function that calculates what is the new expression that we get if we substitute b for x in A. And why is this? Why am I talking about this? Why is this a story to talk about? Well, the problem is that there's too many ways to do this, right? It's not that we don't know how to do it. In fact, we know how to do this too much, right? And if you start looking around, you'll find you're just kind of overwhelmed with number of different answers for what is the variable type, how do we represent the binder, how do we implement substitution, and they're kind of differing in the answers to the filling in the blanks in that Haskell code I showed you, and they also kind of differ in how you use it. Once you've defined these operations, you're not done. You still have to use them in the correct way, right? So you might ask at this point, why do we have so many different operations? How could we have such a wealth of approaches, right? And part of the reason is that people have developed all these different approaches to implementing variable binding and capture avoiding substitution because they have different reasons to do that implementation. Maybe they're implementing a compiler or a type checker, or maybe they're just trying to explain how these operations work to their students, or maybe they are proving properties about a programming language. And these different goals are in tension to each other because what is good for one goal may not be as good for a different role, right? So a representation that is really good for proofs is one that's going to be very easy to reason about, that's very pure, that's structurally recursive, but that may not be one that is easy to implement. It may not be one that is fast. Implementing lambda calculus capture avoiding substitution, it's tricky, and it's notoriously tricky, and very impressive people have made mistakes here. So picking representations that are less error prone is an important criteria when we're thinking about these different implementations. And once we have implemented capture avoiding substitution, we still have to use it correctly. And you could also have mistakes, maybe some global invariance in your representation. And then finally, if you're putting this as part of some kind of implementation, performance is important. Now, if you're like me, you want everything, right? So if you want something you can reason about, you want something that's correct, you want something that is fast, you want something that is easy to use, how do you figure out, which one of those many different implementations that I showed on the previous slide, which one is going to check all the boxes? Right. And notably, I'm going to talk a little bit about performance here because I've done some benchmarking, but I also really do care about proofs. So that kind of rules out from the beginning some very imperative algorithms based on updating graphs. Those are not really in scope. I'm working in the context of Haskell, where everything has a very pure mathematical definition. Okay, so how to answer that question is to sit down and try to compare these approaches carefully. And part of my inspiration, so I'm not going to start from scratch, is I have found this draft paper by Leonard Augustin. So it's, maybe it's almost 15 years old now, or over 15 years old now, and never really published, but it's available. And the paper itself, it's actually a literate Haskell program, right? So not only does it describe 4 different implementations of capture avoiding substitution, but it also provides complete source code and a very simple benchmark. So that's kind of my starting point for this exploration, is I'm going to start from these implementations, but let's go a little bit deeper and try to see what we can understand about them. Right. And in particular, what I'm going to do is I'm going to take today, and what I'm going to tell you today is I'm going to take 2 of the implementations from Leonard's paper. So the one based on just names and simple renaming, and one based on de Bruijn indices. And then I'm going to add a third approach to variable binding to capture avoiding substitution. That's one that I'm familiar with that isn't in Leonard's paper, that's based on the locally nameless representation. And this one is kind of a mix of the first 2. It mixes names and indices. And I'm going to give you an overview of that and kind of point out how they compare to each other. And we're also going to compare how their implementations work in terms of performance and how they are similar to each other, right? And what we're going to find is that we're going to start with a sort of very straightforward implementation, but we're going to see if we can make it a lot faster by adding some optimizations to it. And this works for all 3 of these different versions. And we also can see that since I'm worried about correctness and making it so that everybody can implement the lambda calculus quickly, we can also make these 3 different implementations more generic by making a library version so that they're easy to add to not just my implementation of lambda calculus, but everybody's implementation, no matter what the language is. Okay, so to start off, I'm just going to give some examples of using these 3 different representations of variables and binding with normalization function. Right, so this is looking at these 3 different representations through example. And some of this may be review, especially if you've seen the lambda calculus before, but I think it's really important to kind of look at how this works carefully, because that's going to show up later when we think about how to optimize it. Right, so the first example, so this is I'm going to do the same lambda calculus term each time. We're going to normalize this term. It has 1 beta reduction in it. So if you can see my mouse, we have this function inside that is applied to this argument. That's the beta reduction we're going to do. And to make things a little bit clear, I've colored the variables. So the blue y is bound, all occurrences of the blue y are bound to this lambda that is also blue, whereas this is a different y and it's bound to this brown lambda. And we have a gray X and a black X. And so those are different uses of X. These X's correspond to the gray X. Okay, so think about, so how are we going to normalize this lambda term to do this instance of capture avoiding substitution, right? And so here what we're trying to do is we're going to substitute this triple X term for the blue Y inside this body of the term. Right, and so as we do that, the result we get, it looks like this, right? We've replaced each blue y with this triple X term, but we didn't replace the brown y because it's a different y. And we also had to rename the black X to be a new Z because we didn't want to capture these gray X's, right? So we've done some renaming to avoid capture, and we were actually able to kind of stop our operation of substitution because we got to the point where there weren't any more blue Y's, right? And we knew that because we got to a lambda that bound a Y. Okay, so this is kind of capturing a lot of the ideas of what's going on if you are working with a representation that just uses names for variables and names for binding. Let's look at the same thing if we are using de Bruijn indices, right? So, oh, we have a question. So thank you for that question. Does the example term has its own name and reference? I'm not sure I understand the question actually in the chat. Or is it the original? This is an example I just made up for this talk because it kind of shows a lot of things going on with each of these three different. Don't try to think about what it does. It doesn't do really anything interesting. It's just there to kind of demonstrate different situations that we're going to encounter with these different representations. Okay, so now we have another example. And now this time I'm going to represent the same lambda term that we just saw with names. I'm going to represent this lambda term with de Bruijn indices. And so there, I've kept the colors the same, but now I've gotten rid of the names at the binders, and I've replaced the names at the occurrences with the index to what binder they go with, right? So, and you can just verify to yourself, like for example, this purple 2, you have to skip over 2 lambdas to get to the purple binder, right? And now this is the representation that an implementation of capture avoiding substitution with de Bruijn indices has to work with. And so what are we trying to do in this situation? Here, we're trying to do the same beta reduction, but this time we're going to be substituting this 000 term for the blue 0 variable, right? The variable that corresponds to this blue lambda, right? And when we do that, this is our result. And when you see this result, you can see that 2 things happened, right? So one thing that happened when we were doing de Bruijn indices is that depending on where the variable occurred that we were substituting for, we had to change the term that we were substituting in, right? So we started looking for the blue 0, but then we went under a lambda, and then we had to look for a blue 1. So that meant this occurrence, it's under more lambdas. And so we had to increment the variables in the term that we were substituting. And so even though we started substituting 0, 0, we ended up substituting 1, 1, 1. The other thing to notice is that if you look at this 2, 3, and 4, right, they got decremented to 1, 2, and 3. And that happened because, well, we did a beta reduction. We got rid of this, we got rid of this blue lambda. It's not there anymore. And so everything that was pointing outside that blue lambda was now pointing outside of 1 fewer lambdas. So we had to do a decrement operation there. So as we were doing this substitution, that also, it's not just finding the right place in the term for this new expression. It also involves some index manipulation, either increment in the term that we're substituting in or decrement in the term that we're substituting into. Now, the last example is a locally nameless representation. And this is a representation that mixes de Bruijn indices and names. So the idea in this representation is whenever we look at a term, the bound variables are going to be represented by indices and the free variables by name. So that means when we start and we think about how reduction works for the same example, we're going to start with the same starting place that we did for the de Bruijn index example, right? But we're going to work with it a little bit differently. We're not going to do the reduction immediately. What we're going to do is we're going to go into this term and we're going to turn these outermost bound variables into free variables before we do any kind of substitution. So our very first step is to name these bound variables and turn them into names, right? So I'm going to happen to pick W and X for those, right? So I'm going to pick W for the purple bound variable and X for the gray bound variable. And so the first step is to kind of expose this beta reduction. And then when we do substitution, we're going to be doing substitution under an invariant. And the invariant that we have for substitution is that the term that we're substituting in, it doesn't have any dangling indices, right? It can have some indices, maybe there's some bound variables inside of it, but it doesn't have any variables that refer outside of that term, right? And you can see that this particular term satisfies that invariant because we've named all of these zeros that point outside that term, we've named them X before we do that substitution, right? And so once we do that, now we're going to substitute this term, this triple X term, for this variable. It's still bound, right? We're going to substitute that for 0 inside this other term. And so after we do that substitution, we're going to put those terms in for either 0 there, or we go inside of a lambda for 1, and we'll get this result. But now we're not quite done yet because we started by peeling off those outermost lambdas. We have to put them back in. So the last step is to close it up again and do the opposite transformation where we took the names X and W and rebind them with 2 bound variables. And so we end up in the same place as we did for the pure de Bruijn definition of capture avoiding substitution, but we had to get there in a different route. And we did a little bit less shifting in the middle of substitution, but we had to do this additional opening up and closing before we got to the substitution itself. So there's another comment in the chat. The color scheme itself seems to be our approach to tackle the problem. You can kind of view the color scheme as a variant on names. I don't think it's going to be a full approach, but that might be something to look in. I'd love to talk to you more about that afterwards. Okay, now one thing to notice for all 3 of those examples is we had to do quite a bit of bookkeeping, no matter which approach we chose, right? So when we had names, we had to rename the bound variable. And what does it mean to rename a bound variable when we're avoiding capture? Well, we had to first notice that we were going to capture. And so that involves calculating some free variables in A to figure out what could possibly be captured. And then when we rename, we had to pick a new name. And so we had to know what names we could choose from, what name is sufficiently fresh. And there has to be some mechanism for picking a fresh name, either working with free variables or keeping track of names that we've used, or both. With the Bruijn indices, we had to do shifting, right? So you saw that as we put the term A inside while we were substituting it in, we had to shift its free variables as it got deeper inside of the term we were substituting into. And then in B, we had to decrement some indices because we did a beta reduction. We lost a binder. And then finally, in the locally nameless term, while we were doing capture avoiding substitution, we didn't really have a lot of bookkeeping there, but we did have some before and after, right? Because we wanted to maintain this invariant that we weren't working with terms that had these dangling indices, right? They were always replaced with free names. But then we had to do a lot of swapping where we would change indices into names and names back into indices at the right point, right? So you can see that even though substitution looks like this simple structurally recursive thing, there's a lot going on behind the scenes when we're doing a correct implementation of it. Right. So the next part of the talk is I want to talk about, we've looked at how these three different approaches work with on examples of substitution. Now let's step back a little bit and look at how we use them if we are in some kind of context where we have our expression, we've represented our lambda terms. Now we want to do something with it. We want to use substitution for something, right? And the thing that we want to use it for is reduction. So we're going to look at an implementation of lambda calculus reduction using these three different approaches. And this is going to give us a little bit more concrete understanding of what it means to work with these different representations. Right. And in the version of reduction that I'm going to show you, it's called normal order full reduction, right? It's whenever you reduce lambda terms, you kind of have to pick what order you're going to do in. Are you going to reduce first and then substitute, or substitute and first? Are you going to leftmost, rightmost, right? So I'm going to do the same thing that Leonard Augustin did in his paper, which was normal order full reduction, right? Where we're calculating the normal form of some lambda calculus term, right? And we're going to go through and we're going to normalize each subterm, right? So we're going to, variables are already in the normal form. If we have a lambda expression, this is an example I'm showing how we can implement it when we're using some kind of named representation. So in a named representation, our definition of a binder is just going to include the name and the body. And when we normalize under a binder, we just go underneath that binder. We do our recursive call and rebind it. In an application, when we're doing this normal order full reduction, we first have to, if we have an application, we're going to expose the weak head normal form of the first component of the application. And if that happens to be a lambda expression, that's when we're going to do a beta reduction. So if we look for the weak head normal form and find some kind of lambda where we're binding x and some body a0, then we're going to substitute the argument. Before we do any reduction, we'll just substitute the argument for x inside of a0 and then keep normalizing. Now, if it turns out that the head of the normal form of A is not a lambda, if there's no beta reduction there, then we're just going to normalize the application directly. And then what is weak head normal form? That's a lot like just calculating the normal form, but we're going to do fewer reductions, right? So when we're computing the head, we don't really need to recurse underneath lambda expressions. And when we're doing applications, we're only going to if we find lambdas, we'll reduce them, but we'll only be looking at the head of the form. Now, it doesn't really matter so much what the definition of this normalization function is. I'm putting it here so you can see when we're using variables, it's pretty direct to see how to use variables in this particular example. Substitution handles the capture avoidance just fine in this example. Certainly, if you're trying to compute the normal form of a lambda term, there are more efficient ways of computing the normal form. That's not really what the question that I'm trying to answer today. Really, I'm really thinking about substitution itself. Okay, now let's see what happens if we do the same thing with de Bruijn indices, right? And so we're going to normalize an expression that's represented with de Bruijn indices. The variable case doesn't need to change, even though we're using numbers instead of names for variables. That's not really a problem. And when we do a binder, it's very subtly different, right? We don't have a name for the binder because we're representing our variables with names, but we're going to do exactly the same thing. And in fact, in the application case, it also looks very similar. The real only difference here is we have this implicit name, 0, for the variable at the binder. And so that's the variable that we're going to be substituting for. Otherwise, working with de Bruijn indices looks very similar to working with names once you have an implementation of capture avoiding substitution to build off of in this particular example. Things look a little bit different when we're working with lambda locally nameless terms, right? And here, the key difference when we're working with locally nameless terms is what happens when we go under a binder, right? So when we're normalizing a locally nameless term, there is no name in the binder, but before we do our recursive call, we're going to pull this body of the binder out, and we're going to make up a new name for that variable at the binder, and we're going to substitute in to convert the implicit bound variable 0 to a free variable x. And so that's going to give us a body where we've named the variable that was bound at the binder. That's what we're going to normalize. And then, so that's what we use the recursive call for. And then when we're done, when we get that normal form, then we want to close it back up. We want to turn it back into a lambda expression. And so here we have to do a separate operation. And this is not substitution. This is a separate operation that has to be defined for lambda calculus terms with this representation that's going to replace that name with the bound variable 0. So that's the big difference with locally nameless. When we get to the application case, that's going to look the same as we did, though we'll know internally that this definition of substitution is a little bit different than the definition of substitution that we saw with de Bruijn indices, because we know that we're not going to have to do any of the same kind of internal shifting during this operation because we've been maintaining this invariant as we're using with the locally nameless terms. Okay, so that's kind of two ways of looking at these three different approaches to variable binding, both in terms of examples of how reduction works and in terms of some code that uses it and kind of comparing how you need to use this code. But that doesn't really answer the question of, if you care about performance, which one is going to be faster when you right? They all have a lot of bookkeeping that's going on, right? Or how do those overheads compare? Right. And so just to measure this is kind of a simple benchmark, but I'm using the benchmark that was in Leonard Augustin's paper, right? He took the church encoding of this particular expression, right? The expression is the factorial of 6 equal to the sum of the numbers 1 through 37 plus 17? Now, why did he pick this? Well, we're asking the question, really, is 720 equal to 719? And so when we normalize this term, we're going to get the church encoding of false. They're not equal, but we're going to have to do a lot of work when we do it. And I actually took a look at this benchmark to see exactly how much work we do, right? And it turns out we're going to do almost 120,000 calls to the substitution operation whenever we do normalization. And this is independent of whatever scheme that we're using to represent variable in binders, right? You can see that the implementation of normalization, it calls substitution in the same place. And so it's going to do a lot of calls for substitution. And the term itself is a pretty big term once you do a church encoding of it, right? So in the deepest point, we have 25 nested binders. At the deepest point of the term itself, it's 53 nodes. That's like if you just think about the abstract syntax tree, that's how deep it is, not the overall size. Right, and then whenever we do a substitution, each of these lambda expressions that we're doing a substitution, they do use their argument multiple times, right? Not a lot, but it's not the case that, most of the time we're substituting where variables aren't used or used only once, right? It's more than once. Okay, so let's think about benchmark results. So I took Leonard's 3 implementations, and here I'm really just replicating his paper at this point, right? Because he also ran this particular benchmark on this particular set of code. I did it on this laptop that I'm using to give my presentation here. And what did I find, right? And they're different from each other. Like by the de Bruijn indices was twice as slow as the other two, but they're kind of in the same ballpark, right? They're doing different kinds of bookkeeping, but they all have to do bookkeeping, right? And so it took about, with this big term and these 120 or odd substitutions that it needs to do for its full normalization, it took about 2 seconds in the worst case, right? Now, one thing when we are benchmarking Haskell code is that it's kind of tricky when you are benchmarking Haskell code. And the very first thing before I started even thinking about my implementation of substitution was I was like, well, I'm a little worried about what laziness does, right? And so I took this expression that I wrote like this in Haskell, which is not strict, right? And so it doesn't, this is a non-strict data type, and I added some strictness annotations, right? And since the variable was strict, I could also try to unpack it, remove a level of indirection, right? Let's just see what this does. If we just make our data type representation strict, let's see how that changes our benchmarks, right? And I found that on some of these implementations, it has a pretty dramatic effect, right? Even at, we haven't even thought about getting rid of any of this bookkeeping, but just making the data type strict kind of, for our name representation, it didn't make a huge effect, but these based on indices, somehow it really sped things up. And I don't really have a good answer for why it sped things up. And it's not the case that every normalization is going to speed things up. I've done some benchmarking with some random lambda calculus terms. There it kind of works the other way, where the lazy implementation is faster than the strict one. The strict one actually slows it down. But on this particular example, we see that strictness actually does improve our running time. Okay, so this is kind of our starting point, right? Is can we make these implementations faster? And the answer is yes, right? So you saw there's a lot of bookkeeping. And if I just asked you, come up with ways to make that bookkeeping more efficient, right? You probably come up with some similar solutions to what we have here, right? So I'm going to work with this general idea, like when we're doing in all three of these versions, we had to do multiple traversals, either to rename bound variables or to shift indices or to exchange names and indices together, right? We had to do a bunch of traversals when we just wanted to do a substitution. Let's try to group it together and cache information so that we don't have to do some more. So what do I mean by that? So just for the named implementation, right, instead of whenever we do a substitution, substituting for a single variable, let's substitute for a bunch of variables at once. If we do that, that means that when we have to rename to avoid capture while we're doing capture avoiding substitution, we don't have to do two traversals. We can do that renaming and the original substitution we were doing in all at the same time. You also saw that when we were doing the named representation, we had to detect when we needed to do renaming. So we had to do a lot of free variable calculation. And so another optimization that we could do is hide some information in this bind type. So inside the binder, we could cache the free variables of the body, right? And that can help us when we are doing this, right? Because first of all, that'll help us if we ask for the free variables of the term multiple times. We just have to go until we find the binder, and then it's cached there for us. But it also helps us cut off substitution early, right? So we can tell when we don't need to traverse and substitute inside of a binder, because we know this set of free variables that could be substituted for. Right, so these are some ideas that you could think of to optimize a named base representation. If we look at indices and locally nameless, we can also do similar things, right? So for indices, we could represent not just substituting for a single index, but substituting for an infinite number of indices. And I'm not going to really explain how this data type definition for substitution actually represents kind of substituting for all indices at once, but it's actually a very efficient representation of a substitution for indices in a lambda calculus term. And here I found that if you cache a substitution, so you don't actually apply it all the way, then you can compose substitutions represented in this way very efficiently. So if you have two substitutions at once, and you can see in this particular benchmark that happened a lot, right? Where we have 120 substitutions during normalization. So we're going to be substituting a term and then resubstituting in the same term. Say two of them meet together, we can kind of optimize that. Like if we're shifting once, we can group multiple shifts together, right? And so this is going to help us do fewer traversals of the term and cut off traversals that we don't need to do. For the locally nameless representation, we kind of have a different story of how to do it. And here the thing is, we're doing this opening and closing, where we're going to name variables. We're going to name indices with variables, and we're going to name variables with indices. And so here we can cache these so that we can combine them together. And again, I'm not going to go into the details, but it's the same kind of very high level idea of making sure that when you do multiple traversals of a term, you can kind of glue those traversals, fuse them together, so that instead of doing things sequentially, we can have this sort of parallel traversal of the term. Okay, so how does this work, right? So here, I'm starting with sort of the strict version, right? So if I started with the original one, it'd be pretty hard to see what happens after it's been optimized. But here, even when I'm starting with the strict one, it's still pretty hard to see what happens, right? Notice that we went from seconds to milliseconds on this particular graph. And so these optimizations on this particular benchmark really did have a large effect, right? So we're all the way down to 2.8 milliseconds, right? Or 6.2 milliseconds. And remember, for de Bruijn indices, right, we started with 2 seconds. So we've made tremendous progress here. Right, okay, so that's implementing the lambda calculus so that it runs quickly. But what I didn't really tell you is, like, coming up with these optimized versions, that took me a long time to do. And it took a lot of debugging lambda calculus implementations, which is not really fun to do either, right? And so is there a way that we can make it so that the next time we need to implement substitution for perhaps a different language, it can happen more quickly? Right? And the answer is yes, right? So what we want is, we want this idea of a binding library, a library that is there to help us implement capture avoiding substitution, to give us a definition of variables and binders and help us create a definition of substitution, so that we just really have to talk about how to do a traversal of our term, and the binding library kind of does everything else, does all the optimizations itself. And so I'm going to take this name-based version and talk about, and I figured out how, for all 3 of these different implementations, how we can divide these optimized implementations into simple client code that declaratively specifies where the variables are, where the binders are, and much more reusable but sophisticated library code that captures the ideas of these optimizations to make them accessible to others. Right, so for binding library based on names, it might look like this, right? So the binding library itself is going to say, I'm based on names. So the variable type might expose that it's representing names. This ID int, this is just a type for names that I have, that it represents identifiers using ints for efficiency, but we're going to treat them like names, right? We're not going to, they don't have any reference to the rest of the term. Right, but the binding library, it's going to keep the type bind abstract as an abstract type, and this is important because, remember, part of our optimization was to be able to, like, cache some information at the binder, and so by keeping this abstract, we can kind of hide some cached information that is helping us implement substitution faster, but doesn't really affect the semantics. Right, and we can also, since we're fusing substitutions, we can have an abstract type for substitutions, right? For names, internally, that's this some kind of map, finite map from names to expressions, but we can expose it just as this sort of abstract type of substitutions. And then the library itself really hinges on some type class declarations that talk about here are the operations that the library supports. So the library is going to need some information from the data type, and so that it can talk about how to calculate the free variable of binder or how to substitute through a binder. And then the client can use those operations when it's implementing the free variable and the substitution functions itself. So again, maybe this will make a little bit more sense on the next slide when I show what the client needs to do. The client needs to make instances of these 3 different classes for their expression type. So the first instance is just going to be saying, this is the var constructor for my data type. The second one is saying, here's how to calculate the free variables of the data type. And the third one is saying, here's how to substitute for B's inside of an A. And I have a little bit of a multi-parameter type class going on because we actually do want to change the type B, right? We want to be able to substitute for expressions inside binders, right? And so that's a different type. And that turns out to be more generally useful. For example, if we started to work with a more sophisticated AST type where we might have expressions and commands or types and terms, and we want to be able to substitute flexibly between them. Right, so this is kind of what the interface for the library looks like. And then from the implementation side, the client needs to provide these definitions, but the definitions are dirt simple, right? The client is just it's just a traversal over the expression type, right? So for free variables, it's very straightforward, including the free variables of the binder in the lambda, right? So if you remember, our expression definition said lambda expressions take binders. The library knows how to calculate the free variable of a binder, given that it knows how to calculate the free variable of the body of the binder. It takes care of figuring out, subtracting out the variable bound at that binder. It knows how to do that. And so here we're just using the instance of the free variable class for the binder directly. For substitution, it works the same way to substitute through a binder. And here's really where capture avoidance happens. Internally, the library is going to make sure that this substitution is not going to get captured by this binder. And so that means the client doesn't have to worry about it at all, right? The client can say substitute through the binder when we're substituting this expression. The only tricky part is, since when you substitute a variable, you're replacing a variable not with another variable, you're replacing it with an expression, you have to defer to an extra function, right? A substitution instance for variables doesn't really make sense here. Right, and so this is really nice, right? So it's a very simple traversal, right? Really hiding the complexity. And this is a technique that works. I'm showing how it looks for these name-based optimizations. You can do fundamentally the same thing with the Brown indices and with a locally nameless representation too. And you might say, well, look, those traversals are pretty mechanical, right? They really are defined by the structure of that data type definition, right? There's nothing really smart going on, right? And so also you can go to that library and extend it a little bit with one little bit of additional information, helping the library understand where the variables are in the term. And then all of these operations can be augmented with default definitions that are based on generic programming, where the generic programming, if you derive generic for your data type definition, then you don't even have to say how to calculate the free variables at all. The generic definition can just take over, find the variables, find the binders, and call the right functions at the right time, right? And so that means that really the client only needs to write this code. Doesn't even need to write the definitions of free variables or the definitions of substitution. Generic programming can do this for it, assuming that we've communicated to the library how to construct variables and expressions and how to find variables when they're inside of expressions. Now, I'm going to benchmark this. So for full disclosure, when I benchmark it, I'm going to make sure that I tell GHC to specialize everything. I'm putting a lot of inline pragmas. I think that it's a good idea to use generic programming, but I'm very concerned about the overheads that come from this kind of approach to implementing it. It's not necessary, right? Because you can get a lot of the benefit just by here. This no generic programming for this particular version, right? But I think especially when your data type definition gets really long, if we have much more than 3 constructors and you want to keep things flexible, generic programming is a really good approach. Okay, so let's see what happens with the benchmarks. So again, we're going to expect things to get slower because we've taken something that we have just optimized away, and now we're splitting it apart into library and client code. But the cost overhead is not very significant. Maybe at most it's, we're almost doubling it here for the name representation, maybe 25% more here for DeBrown and locally nameless. But if we step back and look at the big picture, right, the generic programming overhead is much, much smaller than the benefit that we got from optimizing our representation, or even just the strictness and annotations in the first place, right? So that should really not be our first, like if we really care about performance, avoiding generic programming shouldn't be our first thing. Our first thing should be finding a really tuned, optimized implementation to begin with. And then if it turns out that the generic programming is not so great, we can fall back and replace it with explicit instances. Okay, so what have I shown you, right? So I've shown you that we can look at these 3 different implementations of variable binding. We can kind of think about ways to optimize it. None of these optimizations are very new, but we can do that. And then we can divide them into client. We can make libraries based on it. And all of this is available in this GitHub repo that I gave you the link on my first slide. I want to point out that there already are a lot of binding libraries out there. If you look on Hackage, Brent Yorgi and I worked on one over 10 years ago now, right? That one is not really maintained anymore because it's based on template Haskell to do the generic programming. And since template Haskell has been updated, I really don't want to update that library. And the reason that I don't want to update that library is because it's already been ported in Unbound Generics to use GHC generics, right? So already you can use Unbound Generics to get a locally nameless representation. There's also a library based on DeBrown indices by Ed Kmet called the Bound Library. And then there are some libraries out there that are based on names also available. However, if you use these libraries, I suggest you benchmark them, right? Because you'll see that the performance is not all of them have had the same attention to running time. And indeed, on my to-do list is taking some of the ideas of what I've learned about optimizing the locally nameless representation and incorporating it into Unbound Generics. Right? There's still some holes in the story to put it in the full library, especially with pattern binding, but I'm confident that we can take approaches like Unbound Generics and make them more efficient. Okay, so that's my conclusion. Like, we've done a lot. We've done it just with one benchmark, so let's not read too much into it. But at the same time, right, I think one thing that we can learn from this is that, we might sit here and think, okay, should I use names? Should I use indices? Should I use a combination of both? What really is significant is really what you do once you've made that decision, what kind of optimizations that you put into your definition of substitution. And that's really where a lot of the significance. Maybe it's a little bit more difficult to optimize the name representation, but maybe that pays off in other parts of your code in terms where you really would like to have the names there. I think it's really important to be able to not only be able to optimize these definitions, but also to make them accessible, to be able to create a binding library out of it, and especially one that supports some kind of generic programming, to make it easy for people who are just kind of throwing things together to have a correct and efficient implementation of substitution right out of the box, right? This is only part of what I've been playing around with. I've really, I only have a 1 hour talk here. So I can't go into too much details. I've done a lot more implementations than these three. I've looked at lots of different variants. There's no end though. I'm nowhere close to looking at all of them. And it would be also good to look at lots of normalizing lots of other lambda terms and creating benchmarks. I've done some based on random terms, but I would like some help kind of thinking about, what are some good benchmarks here. Okay, and so that's it. And I will stop sharing my screen and start answering some questions. So I see that I have some questions in the chat. Right. Okay,
Yes,
so,
Yes, so there's a question from John Rabbi.
Yeah. Okay, so John's question is, do you have any intuition about why the locally nameless representation is the fastest? Hardly, like the locally nameless representation, it's using these invariants to not have to do shifting inside the term. So once you name the variables, you don't really have to do anything more with them, right? And so that would be my intuition, but I would like to do a lot more benchmarks this to know that it really is the fastest, right? It's the fastest on this particular example. This particular example, has been cooked in a way to do a lot of repeated substitutions to really bring that out. But in this case, it really does point out that kind of grouping together operations like naming, that's very easy to kind of group that together, right? So that's really paid off for us. Okay, should I go to the next question, or how are we going to do this?
Next question is by Jan. I can read it if you like. So the techniques you show use simple types between quotes. Have you thought how they would fit in with languages with more fancy types between quotes?
So you can get really far with fancy types. So I have an implementation for de Bruijn indices and locally nameless that uses fancy types to keep track of the binding levels to make sure that, so for example, locally nameless, we didn't want any free indices in our term. You can use a fancy type to guarantee that. And you can also use that with de Bruijn indices to make sure that you're substituting in the right way. In terms of setting up the class structure, the fancy types don't interfere with the classes. Just the types are a lot more intricate in the classes. But then the next point of using generic programming to automatically derive the traversals, GHC generics isn't so good at these data type definitions with gadgets. And so that part is not available to you. So if there's an extension of GHC generic so that it can deal with index data types more smoothly, then that can take advantage. But you get a majority of the benefit already, even in the context of well-typed lambda expressions. And I do have, I'll just advertise, I gave a talk last year about well-typed lambda terms representing system F using well-scoped lambda terms in Haskell. And there you can see a little bit of what it looks like to define capture avoiding substitution with a well-scoped term.
Okay, so I hope that answers your question, Jan. By the way, I invite people who have questions to simply turn on the camera. That makes communication slightly easier. And I see Robert already did that. So I guess, Robert, you have a question? You don't have a question. Okay, I'm sorry. Thomas, do you have a question?
Yes, indeed. Yeah. So thank you very much for the presentation, Stephanie. I'm curious about the fluctuations you've been seeing when running the benchmarks with and without strictness annotations, and in particular, whether you have tried also this variation with the cached version of the different strategies.
Yeah, I have tried that also, right? And there are still fluctuations too.
Right, so it's similar
yeah.
observations.
Yeah,
Okay.
I'm sorry, I don't have like a chart that kind of shows that.
Yeah. Okay.
now. But
That's
I have those implementations and I could make that kind of chart.
okay. Thank you very much.
Okay, so I think Mial, you have a question?
Yes. Do we need any changes if we want to work with dependent types?
Dependent types where?
So there was this nice talk of, I think, Torsten, about how to quickly implement dependently typed languages by basically leveraging the existing types in Haskell. So I wonder if it would interfere, or we can just ignore it and treat it as independent.
So on one hand, like what I didn't really talk about at all was higher order abstract syntax, right? So taking Haskell's implementation of substitution, inheriting things from the Haskell language into your implementation of substitution, right? So that's yet another part of the story. I have one of Leonard's 4 original implementations is one based on higher order abstract syntax. It starts out faster, but then once we start optimizing things like the index things, the index ones get faster than higher order abstract syntax, which kind of surprised me on the benchmark. So I think there's still a lot to learn about, you know, the efficiency of just inheriting. There's also a cost of kind of working with these sort of shallow embeddings where you're taking things from your host language and using it to implement your object language. Things have to line up nicely, right? And so if you try to just go outside of where things line up, then you might run into trouble there.
Yes, does that answer your question, Mian?
Yeah, thank you very much.
Great. There's a question from Brent, who I hope has recovered from feeling old.
Nope, I don't think I ever will. That's how it works.
Me neither.
Anyway, we've talked about this before, but I thought it would be useful to discuss. I mean, if you're just interested in implementing the lambda calculus very fast, there's other ways to do it that don't use substitution, right? Like using a CEK machine or something that just passes environments around. So why care about substitution?
Yeah, and I totally should have expected this question since you asked me it before.
Yes.
And yeah, so your CEK machine, right? It's for implementing normalization, right? And I'm a little bit more focused than that, right? Like we use substitution for lots of things. Normalization is one of them, right? But I just want to make sure that we have a good building block for whatever we're going to implement substitution with, right? And this is more of an example of, you know, we made this unbound library, and I've liked to have it around, and other people have used it, right? And so why do we use it there, right? Because maybe we just want to implement something that looks like our papers and try it out. And we don't want to have to go through working through some kind of abstract machine to have an implementation that we can play with. Right. Maybe there are other answers. I'd love to hear other answers too. I mean, I don't want to say that if you're implementing normalization for the lambda calculus, this is the way to go, because this is not the way to go. Right. And if you're implementing, say you're implementing the next version of AGDA or the next version of Quark, which has to do a lot of normalizations, this is probably not the way to go. Right. But if you're whipping up something very fast that you want to try out with, but you still want it to be able to run reasonably well, that's the kind of space that I want to provide a good solution for.
Yep, thanks.
Okay. I see Sven Bodo turned on the camera, but there was already a question on the chat, so I'm going to give that slight priority. So Rodolphe Lepigre, I hope I pronounce your name correctly. You could
yes.
turn on your camera.
Yeah, let me turn it on. Yeah, basically, I think the question was already answered. So it was about HRIS, but when I barely finished typing and you had already answered it, so Yeah, I was curious because I'm working on a library, NoCaml, that uses HOAS representation, and that's seemingly pretty efficient. But yeah,
great. Yeah, I'll want to take a look at your library.
cool.
Right, and maybe try to translate it to Haskell and see if I can run the benchmarks in the same context.
Yeah, so it's I mean, if I can say one thing more, it's a library that that tries to rule out exotic functions by constructing terms into a type that's called alpha box. And so there is an extra operation that's called lifting that the user needs to specify that lifts a term of type alpha into an alpha box. So that's the only thing that the user needs to give that's specific to their type, basically.
Yeah. No, I'm very interested. Again, I have really not looked at higher order abstract syntax-based representations very much at all, but I am also interested in them and hope to kind of extend this with those representations as well.
Okay, thank you, Rodolphe. Sven Bodo?
Yeah, thank you very much. Very exciting to see these things discussed. I actually have a very similar question to Brent's question. I'm very fond. We have been doing lots of interactive lambda calculus systems millions of years ago. And there the insight was that if you change the structure of your program by doing super combinator construction, lambda lifting, in essence, then your De Bruijn indices become very cheap to do. Right? So this is not a CAK machine where you have an abstract machine to do this. It is essentially the idea to say, okay, I don't take the lambda term that I want to work with, but I transform it by doing the lambda lifting. And then I have a guarantee that my De Bruijn substitution is actually damn cheap. And so this is why I wish, but I see now where you're coming from to some extent. But I think that would be quite interesting if you're interested in performance. What would be the impact? So for example, in your example, would it really make so much of a difference or not?
Yeah. I mean, I think one thing that I've kind of, self-imposed rules is sort of like, I'm not changing the normalization function at all, right? So it has to implement exactly the same normalization in the exact same order, right? And so sometimes, some of these transformations, it speeds up normalization a lot because it also can save work on normalization, like not, for example, if you normalize first and then substitute, right, that could be a lot more efficient than if you normalize the result after doing the substitution, or each of the terms inside, right? I was kind of given this normalization thing. I'm not going to change how that is, right? So
you say you insist on the redices as they are written, and that's it.
Yeah. Because
okay, fair enough.
I want a playground for people who are interested in thinking about languages, and they don't want to modify their language to be able to do something with it. They want to see what substitution looks like in that language. Right.
Okay.
I mean,
but then why care about performance?
We still run test cases. We still run things, right? I mean, when we're playing with languages, we implement them for a reason, right? And
yeah, but I doubt that if you want to play around with lambda terms and just to see what is happening, you will not run anything that will take ages to do, right? If you have that, then most likely you would be happy, because then the terms are going to be really, really difficult to understand in the first place. And then why would you care if you have a transformation step before to make it happen? But it's just my
yeah. I mean, of course, there's lots of places in the design space, and people are going to use lambda calculus for lots of things, like we've discussed.
Oh, sure.
Right. So,
thank you very much.
So because of time, one final question. So that honor is for Hussein. After answering that question, I want to thank Stephanie, and we can continue discussing in the breakout room. So Hussein, please ask your question.
Yeah, sure. Thank you for the talk. I really enjoyed the variety of cases that you spoke about. One thing that I think is quite important, and I don't know whether you have already addressed that, is an explanation of what's going on rather than the time. Right? Some sort of visualization of the actions taking place at the time where they are taking place, rather than the total time. I mean, we can benchmark the total time, and then we can come to certain guesses about why things happen this way. But we need to have some sort of visualization which we can verify our hunches against. Is there such a thing at all?
I would love such a thing, right? Right. If I had such a thing, I would do it, right? Right. Because my point in doing all of this is to understand this space, right? And
sure.
Right. So I'll throw it out to everybody, how else can we understand this, right? We can work through very small examples, but we're also interested in those very, very large examples, right? And, just visualizing it, just watching that reduce is not very informative, right? Because it's just too big, right? And so what else can we do? And part of it, like maybe we can instrument our normalization or the substitution routine so they can tell us things about sort of the characterization of our benchmark of, it did this, like this particular optimization triggered this many times, this particular optimization triggered that many times. We can look at memory usage, right? We can look at memory usage for particular data structures, right? I think maybe we could get a little progress there, but I would also love to hear other suggestions too.
Right, so well, in the wild, Wolfram stuff actually have very good, visuals. So there might be some chance of taking some ideas from them.
Can you give me a link?
Yeah, well, Mathematica, the famous engineering mathematics thing. And, yeah, they have beautiful visualizations. Yeah. So if you watch one of the many online talks of Stephen Wolfram that are streamed on a weekly basis, then you get loads of these beautiful visualizations. Yeah. So anyway, thank you very much.
Okay, thank you. Yes.
Okay, thank you, Hussein, for your last question. So I would like to conclude this invited talk. So thank you, Stephanie, very much for this very elegant presentation.